Imagine you're a mechanical engineer tasked with designing a high-performance heat exchanger. Your goal sounds simple: transfer as much heat as possible as efficiently as possible. Immediately though, you run into a fundamental law that will dictate every design decision you make, the second law of thermodynamics. This law tells us that heat flows spontaneously only from hot to cold, never the other way around without external work. This is why engines must reject heat and why refrigeration systems consume power. But this isn't just a rule about direction, it's a rule about loss. To understand that loss, we introduce entropy, which in thermal design terms measures how dispersed energy becomes. When heat flows from a hot reservoir at temperature TH to a cold reservoir at temperature TC, that energy spreads out and entropy increases. Critically, entropy can never decrease in an isolated system, meaning every real engineering process generates it. To get more conceptual, we look at exergy and anergy. Exergy is the maximum potential work of a system, how good this system can be. As entropy increases, it destroys this exergy, transforming it into the useless energy quantity, anergy. To quantify entropy, we analyze a control volume using the entropy balance equation, where the rate of entropy change equals entropy transferred by heat plus entropy carried in by mass flow minus entropy carried out plus the entropy generation term sigma.gen. Now instead of just stating this equation, let's use it. Consider a simple but powerful example: heat transfer between two reservoirs. There's no mass flow, and the system is at steady state, so the entropy balance reduces to sigma.gen equals q dot times 1 over Tc minus 1 over Th. As long as Th is greater than Tc, the term in parentheses is positive, which proves mathematically that entropy generation must always be greater than 0 in real heat transfer. This is the second law, not just stated, but derived. This is really where it becomes an engineering problem. If you want to reduce entropy generation to make your system more efficient, you need Th and Tc to be as close as possible, minimizing that temperature difference. But now, let's take a look at the heat transfer equation. Q dot equals U A delta T. If delta T becomes very small, then to maintain the same heat transfer rate, the required surface area A must become extremely large. Visualize this. As your design becomes more thermodynamically efficient, your heat exchanger physically grows, larger, heavier, and more expensive. This is the central trade-off in thermal design. Minimizing entropy generation directly conflicts with minimizing cost and size. Engineers are constantly balancing these competing objectives. In the ideal limit where sigma.gen equals 0, the process is reversible and entropy remains constant. This is an isentropic process, the benchmark for perfection. We use this ideal to define isentropic efficiencies. For a turbine, efficiency is the ratio of actual work output to the isentropic work output. And for a compressor, it is the ratio of isentropic work input to actual work input. These metrics tell us exactly how much performance we lose due to irreversibilities. The second law also sets the ultimate ceiling on performance, max system exergy, through the Carnot efficiency, which depends on only the temperature ratio between hot and cold reservoirs and shows that perfect efficiency through maximum exergy is fundamentally impossible. The most powerful way to understand entropy is through what it costs you. According to the Gauss-Stadola theorem, the rate of useful work destroyed is equal to the ambient temperature times the entropy generation. In other words, every bit of entropy you generate is work you will never get back. So when you design a thermal system, you're not just managing the heat, you're managing loss. The second law defines the direction heat will flow, the inefficiencies you cannot avoid, and the trade-offs you must accept. The goal of an engineer is not to eliminate entropy, which is impossible, but to minimize it intelligently, gathering as much exergy as possible by balancing performance, size, and cost. This mission is what turns thermodynamics from theory into engineering.